NVIDIA just dropped something that completely changes how we run large AI models, and honestly, the numbers sound impossible at first. We are talking about KVzap, a brand new system that cuts memory use by up to 4 times while keeping almost perfect accuracy. And the crazy part is, they open sourced the entire thing. No enterprise license, no waiting list. Just download it and start using it right now. Let me explain why this matters and why everyone in AI is paying attention. Here is the thing. When you run a large language model like Llama or Quinn, the model needs to remember everything it has seen before. Every single word you type gets stored in something called a KV cache, and that cache eats memory fast, really fast. For example, if you load Llama 65B with 128,000 tokens in B float 16, that cache alone takes up to 335 gigabytes of memory. Not the model itself, just the memory needed to remember what you already said. That is more than most entire computers have. And as context windows keep growing to hundreds of thousands of tokens, this problem becomes the #1 bottleneck stopping people from running these models. Now, here is where it gets interesting. NVIDIA researchers just built KVzap, and it solves this exact problem. KVzap looks at every single piece of stored memory and figures out which parts actually matter and which parts can be thrown away without hurting performance. And it does this in a way that works during both the initial read and the actual generation. Most other methods only work during one phase or the other. KVzap works everywhere. Across Queen 3.8b, Llama 3.18b Instat, and Queen 330b, KVzap hit 2 to 4 times compression with almost zero accuracy loss. On the NVIDIA KVpress Leaderboard, it landed straight at the top. Let me break down the numbers because they are wild. On Ruler, which is a long context benchmark with tasks that range from 4,000 tokens all the way to 128,000 tokens, KVzap removed more than 70% of the cache and the 4K and 16K test while keeping the average score within just a few tenths of a point from the full cache baseline. For Queen 3.8b, the best KVzap setup hit a removed fraction above 0.7 on Ruler 4K at 16K. That means it threw away 70% of the memory and the model barely noticed. Similar results showed up for Llama 3.18b Instat and Queen 332b. The compression automatically adapts to. NVIDIA said that the same threshold setting, they saw up to 20% variation in compression across different prompts. That is because some prompts are packed with important information and others repeat themselves a lot. KVzap adjusts on the fly without needing manual tuning. On LongBench, which uses real-world documents across 21 different tasks in English and Chinese, the same thresholds led to lower compression ratios compared to Ruler. And that makes sense. Real documents are less repetitive than synthetic test data, but KVzap still stayed extremely close to the full cache baseline after about 3 to 2 times compression. Other methods like expected attention started degrading on several subsets once compression increased. KVzap kept performing. Now let's talk about AIME25, which is a math reasoning benchmark with 30 Olympiad level problems. And these are not easy problems. They require deep multi-step reasoning. On AIME25, KVzap MLP maintained or was slightly improved the pass at 4 accuracy at nearly 2 times compression, and it stayed usable even when discarding more than half of the cache. Only when they pushed it to extremely aggressive settings like removing more than 90% of entries did performance collapse. And honestly, that was expected. But the fact that it held strong past 50% removal is impressive because reasoning tasks are usually the hardest to compress. Overall, the best KVzap setup per model delivered average cache compression between roughly 2.7 and 3.5 while keeping task codes very close to the full cache baseline across Ruler, LongBench, and AIME25. That is a huge win for anyone trying to serve long context models in production. Less memory means lower cost, faster speeds, more users per GPU. So, how does KVzap actually work? The system built on top of something called KVzap, which is another method that already reached up to 4 times compression with minimal accuracy loss. But KVzap had serious limitations. First, it required running the model twice during the initial read, which made it really slow. Second, it could not be used during the generation phase, which made it useless for reasoning tasks that generate thousands of tokens. KVzap fixes both problems. KVzap is an input adaptive approximation of KVzap. It learns to predict which parts of the cache are important by using small helper models called surrogate models. These surrogate models are either a simple linear layer or a shallow multi-layer perceptron, which means they add almost no extra computing cost. During training, KVzap uses something called KVzap Plus, which is an improved version of the original KVzap. KVzap Plus provides supervision by scoring every key value pair in the cache. Then, KVzap trains its surrogate models to predict those scores directly from the hidden states. The training uses prompts from the Nemotron pre-training dataset. They filtered 27,000 prompts to lengths between 750 and 1,250 tokens, sampled up to 500 prompts per subset, and then sampled 500 token positions per prompt. For each key value head, they got about 1.2 million training pairs and a validation set of 23,000 pairs. The surrogate learns to predict the log of the KVzap Plus score. Across models, the squared Pearson correlation between predictions and Oracle scores reached between about 0.63 and 0.77, with the MLP variant consistently beating the linear variant. That correlation is high enough to faithfully rank cache importance without needing the slow Oracle process. During actual use, KVzap processes hidden states and produces scores for each cache entry. Entries with scores below a fixed threshold get pruned. And here is the key part. Instead of keeping a fixed percentage of the cache like most methods do, KVzap uses a threshold. That means the compression ratio changes based on the prompt. If the prompt is packed with important details, KVzap keeps more. If the prompt repeats itself, KVzap throws more away. It also keeps a sliding window of the most recent 128 tokens no matter what. That preserves local context, which is critical for generation quality. The compute overhead is tiny. At most, KVzap adds about 1.1% extra floating point operations for the MLP variant. That is almost nothing compared to the memory setting. And because KVzap only depends on hidden states, it works in both the initial read phase and the generation phase. That is a big deal. Most compression methods force you to choose between speed during reading or accuracy during generation. KVzap does both. Now let's talk about how this stacks up against competitors. On the KVpress Leaderboard, which compares different KV cache pruning methods, KVzap landed at the top for both Queen 3 8B and Llama 3.1 8B instead. The leaderboard measures accuracy on the ruler 4K dataset against compression ratio. KVzap matched KVzap, which it approximates, while beating 15 other methods including expected attention, duo attention, and compactor. Expected attention did show higher scores on LongBench at lower compression ratios, but a closer look revealed that was driven by outlier accuracy on the track subset, which is a few short learning tasks. On several other subsets, expected attention degraded while KVzap stayed close to the full cache baseline. Higher track accuracy at high compression might actually be explained by the overprompting phenomena. In few short learning tasks, adding more examples can sometimes reduce accuracy instead of improving it. So that outlier results in not necessarily a win. KVzap also outperformed methods like H2O, SnapKV, and PyramidKV, especially in multi-query scenarios. Most existing methods are query aware, which means they optimize the cache for the first query. But when you reuse the cache for a second or third query, performance collapse. KVzap is query agnostic, which means the compressed cache works well across multiple different queries without needing to be rebuilt. That is critical for real-world use cases like chatbots or multi-turn conversations where users ask follow-up questions. Now, in fairness, KVzap is not perfect. It is not training-free. You need to train the surrogate models first, which takes some compute. Most KV cache pruning methods today are post-hoc additions, meaning they get layered on top of the model after it is already trained. In the long run, end-to-end integration usually wins. Just like multi-token prediction is starting to replace ad hoc speculative decoding techniques, future models might bake compression directly into the architecture. But for now, KVzap is the best post-hoc solution available. Another limitation is that while research on the 32 billion model are encouraging, the paper says further validation is needed on larger open source models like GLM 4.7 or Queen 3 235B and on architectures with sparse attention like DeepSeek V3. Evaluation could also be extended to more reasoning benchmarks, agentic tasks, and short context knowledge tasks. But the results so far are strong enough that people are already integrating it into production stacks. And honestly, the implementation is dead simple. NVIDIA released everything through the KVpress framework, which is an open source library that makes KV cache compression easy. The repo includes ready-to-use checkpoints on Hugging Face, so you do not need to retrain anything unless you want to. You can literally plug it in and start compressing. The code is clean, the documentation is clear, and it works with standard Hugging Face transformers, so integration into existing workflows takes minutes, not weeks. What makes KVzap stand out is that it is practical right now. It is not a research demo, it is not a theoretical improvement. It is a working system that you can deploy today and see real memory savings without thanking accuracy. And because it is open source, the entire community can build on top of it. People are already talking about combining KVzap with quantization, mixing it with sparse attention, and layering it into multi-tier memory systems. This is the kind of release that shapes the baseline for what everyone expects. That is where we will wrap it up. One thing I'm curious about now is how this affects the long context rest. If memory compression keeps improving at this rate, we might see 1 million token context windows become normal way faster than anyone expected. Drop your thoughts below. Make sure you are subscribed, hit the like button, and I will see you in the next one.